Hi dear folks, my name is Makumba Gerard of EduMath. In today's video, we are going to see how to use Raphson'S method to find the root of exponential functions. But before we go into it, subscribe to EduMath such that you can be notified of the new videos that we make every day. So let's get straight into it and see you there. Now this here is the Raphson'S formula, and it's the one which we are going to base on in today's video, where small n is equal to 0, 1, 2, 3, and they continue. Let's have an example of the exponential function whose root is supposed to be 4. Example. Alright, our example is here. They need us to show that the equation, this one here, 3x exponent x minus 1 equal to 0, has a root between 0.2 and 0.3. They need us to show that. So we are going to use a sign change here as one of the methods that we looked at. Then part B, they need us to use linear interpolation. Find the first approximation for this root to 3 decimal places. So we are going to see this again, much as we saw it in the previous videos. We are going to see how to use linear interpolation to find that root. Then showing that the Raphson'S formula for estimating the formula of the equation 3x exponent x minus 1 equal to 0 is given by this, is what brought us today, is what is here in our agenda of the day. So let us get started. So we have fx is equal to 3x exponential x minus 1. Now to show that the root lies between 0.2 and 0.3, we are going to use sign change method, which comes after evaluating this function at 0.2 and evaluating the very function at 0.3. So we are going to evaluate it here. So we have f 0.2, this is equal to 3 times 0.2 exponential 0.2 minus 1. So when you press the calculator, you will get, here you are going to get 0.2672. That's what we get. Next we need to find f of 0.3. f of 0.3, this is equal to 3. Where there is x, we are going to put there 0.3. Exponential 0.3 minus 1. So when you press the calculator, we are going to get 0.2149. So this is what we get. This here is a negative. Sorry, this was a negative. So since this is f 0.2, f 0.3. Now since f 0.2 is a negative and f 0.3 is a positive, multiplying the two will give us a negative value, and the negative value is always less than 0. So since f of 0.2 times f 0.3 is less than 0, then there exists a root between 0.2 and 0.3. So we are done with the showing that the root exists between 0.2 and 0.3 using the sign change method. That's part A. Now part B, they need us to use linear interpolation once. With the linear interpolation, we need to extract the table which you are going to use. So we have the table which you are going to use here. So here we have the values of the domain. Here we have the values of the range. So values of the domain, here firstly we have 0.2. Here we have 0.3. The value that corresponds to 0.2 is negative 0.2. 0.2672. Value that corresponds to 0.3 is 0.2149. Now, if there has to be a root which we are calling x0, which is the initial approximation or the first approximation, as the question refers to it. If x0, which is the root, is supposed to be here, then f(x0) is gonna be a 0 there. Now we use linear interpolation, and while you're using linear interpolation, remember you have to put in mind the idea of gradients. So I'm going to have gradient AB is equal to gradient AC. I'm shortening this to just grad. Hope you really understand it. So gradient AB is equal to gradient AC. So this is A, this is B. We are getting the gradient. So 0 minus negative 0.2672 divided by x0 minus 0.2 is equal to gradient AC. A is here, C is here. So we start, this here is 0.2149 minus negative 0.2672 divided by 0.3 minus 0.2. So when we work on this, 0 minus negative, this is going to give us a positive 0.2672 divided by x0 minus 0.2 being equal to, when you subtract here in the numerator, we shall get 0.4821 divided by 0.1. So we are going to cross multiply. So when you cross multiply and you multiply through everything, you shall have 0.4821 x0. Then this very one times 0.2, we are going to get minus 0.0964 equal to 0.0267. So when you work out well there, you'll get x0 as 0.2554. But they needed this to 3 decimal places. So that means we have to write our answer to 3 decimal places. So when you round this off to 3 decimal places, x0 is gonna be 0.255. This is to 3 decimal places. So we are done with part B. Now we are going to part C, which requires us to show that the Newton-Raphson formula for estimating the root of the equation, this one here, is given by this formula here. So we are supposed to derive this formula. So again, the Newton-Raphson'S formula is here. So that means it is our task. It is our task to, it is our task to strive and find fxn, f derivative xn. That is the task which we have. So let us get started. We have been given that fx is equal to 3x exponential x minus 1. That is what is given to us. Now this here is a continuous function. Now to make it discrete, we are going to put in small n, subscript n, okay, because you can see that n is taking on certain values which are 0, 1, 2, 3. So this shows that we are going to evaluate this, okay, this formula here at particular points. Evaluating it at particular points means that you are discretizing it. Discretizing it means you are making it a constant. So let us make it a constant. We shall have fxn. So wherever there is x, we are going to put there xn. This is giving us the xn exponential xn minus 1. Then when it comes to f derivative xn, you don't differentiate this because this is a discrete function, and a discrete function is always a constant function. So we shall be differentiating a continuous function. So we shall have to get f derivative of x. F derivative of x. Now when you look at this point here, this here is having two functions of x. We have 3x and we have exponential x. Or someone can say we have x and exponential x. It's the same thing. Now here, when you are differentiating this, we shall apply product rule from paper 1. So we are going to hold on 3x, we differentiate exponential x. So when you differentiate exponential x, you get exponential x plus, I'm now going to hold exponential x, differentiate 3x. Differentiating 3x, you get 3. Differentiating a constant, which is -1, you get 0. Let me pull out the common factor here. So we have f derivative x is equal to, common factor in both of these terms is a 3 exponential x. 3 exponential x out into bracket. Here will remain with the x plus here will remain with 1. So this will lead us to f derivative xn. F derivative xn, this here is equal to, where there is x here, we are going to replace there xn. So we shall have 3 exponential xn into bracket xn plus 1. Then let's bring our beautiful formula for Newton-Raphson'S method. Xn plus 1, this being subscript, is equal to xn minus f of xn divided by f derivative xn. Now let's substitute. We shall have xn be minus fxn is here, so we shall have here 3 xn exponential xn minus 1, this here divided by, this is fxn, don't forget, divided by the derivative, which is 3 exponential xn into bracket xn plus 1. Next we are going to get the LCM. So we are going to get the LCM there. LCM, this is over 1. It's going to be 3 exponential xn into bracket xn plus 1. So this denominator divided by 1, you get this very 1 times xn. We shall have xn multiplying this, so we shall have 3 xn exponential xn into bracket n plus 1 minus this denominator divided by that very one, you get 1 times the whole of the numerator. We shall have to get the numerator. Don't forget that this negative will have to affect this negative. So we shall have 3 xn exponential xn plus 1. Opening brackets here, we are having 3 xn squared exponential x plus this multiplying by 1, 3 xn exponential xn minus 3 xn exponential xn plus 1, everything over 3 exponential xn into xn plus 1. So these are the same terms. In the numerator we shall remain with 3 xn squared exponential xn, don't forget, plus 1 over 3 in exponential xn to bracket xn plus 1. Yes, there we are, and this gives us plus 1, where that smaller n is equal to 1, 2, is equal to 0, 1, 2, 3, they continue. So this here is what was required of us to be shown in the question in part C. We have managed to show that in part C. Now in part D, they want us to use this formula here, the formula which we have got, which is the same as this, to find the root of the given equation correct to 3 decimal places. Please don't forget that 3 decimal places is very important in this question. Why? It determines the maximum error that we have to find. So part D, first of all, let's start with the maximum error. Maximum error, this is a half times 10 power negative n, but n is the number of decimal places. And we have 3 decimal places, so this here is -3, which gives us 0.0005. That is the maximum error. From part B, we calculated the x naught, or the first approximation, which is 0.255. We calculated it using the linear interpolation method. This here is our x naught, or the first approximation. So we calculated it using the linear interpolation. There we are. So next we are supposed to work on this. Remember the use of the error, we only continue if the error permits us to continue. If the calculated error is less than the maximum required error, then we stop. But if the calculated error is greater than the maximum required error, that means we should continue carrying on the computation. So we shall start with n equal to 0 here. When smaller n is equal to 0, we shall have, when you put here smaller n equal to 0, 0 here, we shall remain with x1 being equal to 3 x naught squared exponential x naught plus 1 divided by 3 exponential x naught into bracket x naught plus 1. Okay, now what is x naught? X naught is here, we computed it. So we shall have x1 being equal to 3 into bracket x naught, which is 0.255 squared exponential 0.255 everything plus 1 over 3 exponential 0.255 into bracket 0.255 plus 1. So when you compute on the calculator, we are going to get x1 as 0.2576. This here is x1. Now before we continue, let us check on the error. It is only the error that allows us to continue. So we have error. This is going to be x1 minus x naught and a magnitude. So we have 0.2576 minus 0.255 and a magnitude. There we shall have 0.0026. When you look at this value, it is greater than the maximum required error, which is 0.0005. So that means we should continue. So we are going to say when n is now equal to, this was 1, that was 0, now this is supposed to be 1. So we shall have, put in the other formula, we shall have now x2 being equal to 3 x1 squared exponential x1 plus 1 everything divided by 3 exponential x1 into bracket x1 plus 1. But what is x1? x1 is this value here. So we shall have to substitute in just like the way we substituted for this here. x2 is now equal to, let's substitute in for x1, shall have 3 into bracket x1, which is 0.2576 squared exponential 0.2576 plus 1 over 3 exponential 0.2576 into bracket 0.2576 plus 1. So when you compute very well, x2 is gonna be equal to 0.2576. That is x. Now let's look at the error. So the error here is the magnitude of now x2, which is 0.2576 minus x1, which is also still the same value, 0.2576, and a magnitude. So that means we are going to get the error as 0, which is less than the maximum required error, 0.005. This implies that the root is, they said we give it to 3 decimal places, 0, this one here, but to 3 decimal places, so it will be 0.25. so this here is the root of the equation. So we are done with all the parts of our question here. Next, we are going to have an exercise, a tryout numbers. So here are our tryout. First delete that and you resize. So here are our tryout questions. There are 4 questions. Please endeavor to go through all these questions because they are very important as in terms of the psychomotor domain. So please, thank you for being with me here on my channel. Please subscribe to it. Recommend as many friends as you can so that we can move together as mathematicians. Keep sharing with your friends, and I am very glad that I have you as part of my audience. Please stay with me, and thank you very much.